The short video will take you through writing the formula of organic compounds. You should be on page 5 in your notes, and please follow along with your notes and obviously write in as we go. The first type of formula that you might encounter is what we know as the molecular formula, and this is not one that's used very often. All molecular formulas do, you might remember from your stoichiometry last year, is that they indicate the number and type of each atom in a molecule. And we don't use it much in organic chemistry because it doesn't tell us anything useful like the bonding or the functional group. But anyway, let's have a look at what the molecular formula might look like for propanoic acid. We start off by looking at the carbon atoms, and we see that there's 1, 2, 3 carbon atoms, so C3. Hydrogen, there's 3 there, and 2 there is 5, and 1 there is 6. So it's H6, and there's 1, 2 oxygens, so O2. So C3H6O2 is the molecular formula for propanoic acid. If we have a look at methyl ethanoate, again, if we count carbons, you'll see that there are 3 carbons, and again 6 hydrogens and 2 oxygens. So you see that these 2 compounds, propanoic acid and methyl ethanoate, both have identical molecular formulas, and yet they're obviously very different and have different properties. And that's part of the problem of molecular formulas. You'll learn later that these are examples of something called isomers, but we'll get to that later. The second way of representing formulas is via a 3D representation. If we consider the compound like methane, we might represent methane on a piece of paper like that. Methane is CH4. But what we lose in a diagram like that is the fact that methane is a 3-dimensional molecule. And if you look at this image over here, you can see this ball and stick model shows the 3-dimensionality of a methane molecule much better. This image shows the bonding in methane, and I hope that you can remember that carbon has sp3 hybridization, so this lobe over here is an sp3 orbital. There's the other side of it, and again there's another sp3 orbital, there's the third one, and there's the fourth one. And each orbital overlaps with an s orbital of hydrogen, there, and there. So that overlap there, where the bond takes place, is a single covalent bond, and it's a sigma bond, you might remember, and it's an overlap between an S and an sp3 hybrid orbital. But that bonding clearly shows, and you can see it in red here, that the methane molecule takes on a tetrahedral structure, and it's that 3-dimensional tetrahedral structure that we're interested in representing. This image just shows you the tetrahedron that forms around the molecule. There's the tetrahedron, and if we have a look at the angles, you might remember this from last year, that the angle involved in an HCH bond in methane is about 109 degrees, so that angle over there is the one that's about 109 degrees. So the issue that we have is when you're trying to represent this 3-dimensionality on paper, it's quite hard to do. So we've got a little way of doing that, and in your notes you'll see that we indicate solid lines as whoops, let's just go back. Sorry. Oh dear, let's get back to the right slide. Okay, here we go. We indicate solid lines to show bonds that are in the plane of the paper. Then we use dashed lines for bonds that are pointing away from us, and we use wedge shapes for bonds pointing out towards us. So remember, this central atom over there is the carbon atom. Let's imagine that that bond there and that bond there are in the plane, and so we would indicate it like that. This one you can see is coming out towards us, and so That's this one here. We use a wedge shape to indicate this bond's coming towards us, and that one's kind of going backwards into the page, and so we use a dashed line to indicate that going backwards. So that's a three-dimensional representation. Again, we don't use that very often, but it's an important one to know about. The two that we use most often are the condensed structural formulas and the structural formulas, and they get confused quite easily, so you do need to be careful of the wording. Let's start with the condensed structural formula. Propanoic acid is given, and this is the formula over here. And the way we write the condensed structural formula is to go one carbon atom at a time. So let's start with this carbon atom over here, and we indicate what's bonded just to that carbon atom, and there is 1, 2, 3 hydrogen atoms, so CH3. Then we go to the next carbon atom, that one over there, and there are 2 hydrogens bonded, so we indicate CH2. And then we go to the final carbon atom over here, and we have an oxygen bonded to it, that's that one there, and then we have an oxygen there, and a hydrogen. And so that then is the condensed structural formula of propanoic acid. If we do the same thing for methyl ethanoate, starting from the left on that carbon, we would write out CH3, the next carbon has an oxygen, then there's another oxygen, and then there's a carbon with 3 hydrogens. And that then would be the condensed structural formula of methyl ethanoate. The full displayed structural formula is probably the most common one and the one that we're going to use most often. Let's use ethanol as an example. Its condensed structural formula is CH3, CH2OH. And if we had to draw it out, we would start with that carbon, and it's attached to 3 hydrogens. And each line that I'm drawing there represents a single covalent bond. It's then single bonded to another carbon. It has 2 hydrogens attached. And then it's attached to an oxygen, which again is bonded to another hydrogen. And that then gives us the full displayed structural formula of ethanol, showing all the bonds. If we just bring in an image of ethanol, you'll see that it obviously looks very different because the image here shows the three-dimensionality. We had drawn something that looked like this, and it's common for us to draw these in straight lines. You'll see from the bonding here, those 2 carbons happen to be in the straight line, but because of the nature of the bonding around this carbon, there's an angle there up to the oxygen, and again another angle there, and that has to again do with the orbital arrangement around the oxygen. But just be aware that even though we draw them as straight and flat-looking molecules, they do have a three-dimensional nature to them. Butane's another good example of this. If we had to draw butane, it's got 1, 2, 3, 4 carbon atoms, so we can just draw them in a straight chain. There are 4 carbon atoms, and the first carbon's got 3 hydrogens around it, second has got 2, third also 2, and then the end carbon again has got 3. And that's how you would commonly see a representation of butane. But of course we lose the three-dimensional structure of this, and it's important for you to remember that butane actually looks like this. When carbons are bonded in a straight line, one after the other, they actually don't have a straight line arrangement. They form these zigzag patterns, and that's because of the sp3 hybridization. So whilst we might draw the butane backbone in a straight line, actually it's in a zigzag pattern like that. All right, let's just go on to when you are drawing the structural formulas, you do need to indicate the number of bonds around each atom, and so it's probably useful at this stage for us just to quickly remind ourselves of the number of bonds around each different type of atom. And around carbon, it's in group 4, and it's sp3 hybridized, and so it makes 4 bonds. So whenever you draw a carbon atom, you need to ensure that there are 4 bonds coming out of it. Hydrogen's in group 1, it's got 1 valence electron, so it's looking to share 1 more, and so it just makes 1 bond. So every hydrogen atom must have a single bond coming out of it. And then oxygen is in group 6. It's looking to gain 2 electrons for a full octet. So every oxygen atom would have 2 bonds out of it. Sometimes that could be a double bond, or it could be 2 separate single bonds. Alright, it's time for you to have a go. Activity 4 in your notes asks you to draw some of these structures. Have a go, draw them in the boxes provided, and then your teachers will check that with you.